Okay, so this lecture is about the Tietze extension theorem. And as simple as the name given, right, it is an extension theorem, and we're going to prove this theorem. So the statement is that for any normal space and for any closed subspace of X, for a function, continuous function that maps from A to a closed interval in R that is continuous, we can extend to a continuous function G such that its domain is from the entire space X to AB. And similarly, if you're from A to the entire R continuous, then you can extend to a continuous G that is from X to R. So it basically states that if X is normal, A is closed subspace, and F is a continuous function, then it can be extended to a continuous function that is defined on the entire space. Okay, so this is the theorem, and it is an application of horizontal lemma. So the idea of the proof is that we're going to construct a continuous function defined on X and converges uniformly, say, to G. So then we know that G is continuous, and then again we show that Sn restricted on A, right, approaches to F. So by the uniqueness limit, F and G of A are the same. Okay, so let's begin. So the first step, we're gonna develop some results. So without loss of generality, we can assume F maps from A to closed interval negative R to R because homeomorphism, right? So our claim is that there exists a function such that it is bounded by 1/3R. Okay, so for example, we can picture this negative R, and this is R. Then all the G will be lie inside here, and FA and GA, for any A and A, in particular if you're in A, then the distance between G and FA is less than equal to this. Okay, so to construct such G, we first divide this interval as a length of 3 intervals, and each of them with length 2/3R, because this length is equal to 2R. Right? We divide into 3 sub-intervals, which is like evenly divided by length. Okay, is divided evenly by length, and we let B be the pre-image under, right, I1, and C be the pre-image under I3. They are closed, right? They are closed in this set, right? They're closed in this space, and F is continuous, which means that B and C are closed in A, but A is closed in X, so they are closed in X. Because they are trivially disjoint, we can apply horizontal lemma, right? Because we have X is normal and disjoint closed sets, then we can separate them by continuous function. Say the separation function is G, and that's from X to we can take it to any closed intervals, right? So we let our intervals be negative 1/3R to 1/3R, such that it takes B to this and takes C to this. Okay, so separates B and C here. Now, from here already we know that Gx is this desired thing, right? And for the second condition, well, for any A and A, if A is in B, then FA is, right, obvious in here. Right, this is definition, right? F of A for A and B, 0 in here. Right, is in I3. Sorry, it should be I1, right? Yeah, it should be I1. Okay, so FA is in I1, and GA is obviously equal to this Y. Well, right, it's definitely also I1, which means that they all lie in I1, and the length of I1, remember, is 2/3R. Right, and for A and C is by symmetry, and otherwise we know that here first we have F from A to negative R, right, if you're not in B, you're not in C, it maps into this, right? And also G is itself a function, right? It maps this. And F, right? If you're not in B, you're not in C, then you must map in here. So it coincides. So again, right? So we proved the existence of such G, right? It is kind of like, it's like shrinking, right? It shrinks and approaches F. So we're going to prove part 8 of the theorem. So remember, the part 8 of the theorem is that if you're from A to closed interval, then you can extend to the entire space to the closed interval. So with a loss of generality, we can assume that it produces -1, 1, right? And then we're going to apply step 1 such that when R allowed right now, R is equal to 1, right? So this, blah, blah. And now we consider this difference map. F1 minus G1. It is again a continuous function, right? Because the sum and product of continuous functions are continuous, even for its domain is a general topological spaces. Doesn't matter. And for A, right, F and G, like from here, we already see that F minus G1 is function from A to, right, -0, 3, and 2 over 3. So here, again, we could apply step 1. There is another function G2 such that G2 is in 1 over 3R and 2 over 3 times 2 over 3, right? R is 2 over 3, so this, right? F1 minus this. So as you can see the pattern, right? In general, suppose we have n of the functions such that you're like this, right? Less than equal to 2 over 3 to the power of n for any a and a. We define Gn plus 1 such that it is equal to 1 less than equal to 1 over 3 of this, right? And Fa minus subtract minus until G minus 1a, it is 2 over 3 to n plus 1 for any a and a. So as I stated before, right, it's going to shrink. And we're going to define G as the series of this Gn. Well, to make sure this series converges, we can say that it is bounded, right? It's by comparison test. I mean by comparison test, I mean like this thing we can keep estimate is less than 1 over 3 of the series, right? 2 over 3 of n minus 1. But this is all a constant, right? It's a constant, right? It's a geometric series, so it converges. It's a constant, and this is monotone converges. It is monotone, right? And it is bounded, so monotone and bounded converges, right? So this converges for, right? It converges for all x. So G makes sense. Now we just, for convenience, let Sn to be the partial sum of the GKs. Well, it is definitely continuous, and by the Weierstrass M test, right? From here, we can already see that by the Weierstrass M test, right? It's less than some constant, right? I mean this here, right? Because this bound works for all x, so by Weierstrass M test, right? It converges uniformly. So Sn converges uniformly to G, which means that the G is continuous because Sn, they're all continuous. Okay, so we have found a continuous function G that is defined from what? The entire space, right? The entire space. Because, yeah, I think, yeah, from the entire space. I mean, I should be more consistent with the notations here. So let me just add a Gn plus 1 from the entire space. Sorry. Entire space to, I think it's, okay. I think it's like something this, right? But I'll just say R for convenience, right? For convenience. I'll just say R. But remember that the domain is X, the entire space X. Okay. And now we want to see that G restricted to A is equal to F, right? Well, this is basically, right, f of A and Sn of A is equal to this, but remember this is really like by our definition here, right? Fa minus is less than equal to this, right? So from here, Sna this, we see that Sna converges to f of A, right? So by the uniqueness of limit, right, Fa is equal to Ga. And to show that G is actually maps in this closed interval, right, we just kind of scale it, right? Let R be the scaling function, right? Just if you're in between 1, you're good. If you're outside of A, you just normalize it. Just make it to the inside the unit interval, right? So this is definitely a continuous function, right? This is definitely a continuous function. And R of G, right, the composition is also continuous. And it is a mapping from X to -1, right? Because G is from X, right? G maps from X to like R, as I say, and little r maps R to -1, right? And that again maps to -1, 1. So it maps from X to -1, 1. It is a continuous function, and R of G of A is R of G of A is equal to Ga, and Fa coincides. And remember, Fa, we don't have to scale it, right? Because we already have that in between. So this is part 8, the first half of the proof. We're already done, right? And the second half is not that long. By topology, right? Because the entire space R is homeomorphic with open interval -1, 1. So right now, if we have F from A to open interval, we can expand the range of F, right? Which remains continuity. It is continuous. Then we can extend F to function G, right? By the way, we already proved it, right? If this is continuous, we can extend it to G. But we want this to be an open interval, right? So how do we do this? So here's how we're gonna do it. So first we let G be the pre-image of the extreme points, -1 and 1, right? We take their pre-image, and of course they're closed in X because this is closed and this is closed, right? Finite sets are closed, right? Finite sets are closed, and as Ga is equal to Fa by assumption, and Fa is contained in this, which means that A and D are disjoint, right? A and D are disjoint. They're closed in X. D is closed in X, A is closed in X. Apply horizontal lemma, we can separate them by a continuous function, and we can make this interval for 0 and 1, such that phi of D is equal to 0 and phi of A is equal to 1. Okay, so this becomes D, this becomes A, right? We separate it via continuous function. And we define H as the product of them. It is a function defined on all of X, right? G is also defined on all of X. This also defines all of X. So H is defined all of X to reals, right? We don't know yet. Defined to reals is a product of the continuous function, which is continuous, right? Okay, let me just put it here. And we want to show that it is the extension of F such that restricted A is equal to F. But this is really easy because we have this, right? Right. G is equal to Fa, right? By assumption, right? And to show that it maps to this, right? If it's equal to F, but we have to show that the range is contained inside this. So if X is in D, right? If you're in D, right? If you're in D, then remember this. If you're not in D, well, because we already know that Gx, right? We already know that G is this, right? Oops, sorry. I mean, yeah, because you're not in D, right? So G can only be in the open intervals because you're excluding the inputs that maps to the endpoints. So excluding D, you can only be strictly less than 1. And h of x, right, is less than or equal to 1 times this, because psi is less than or equal to 1, right? Is less than or equal to 1. 1 times this, which so h of x is less than 1. So we're done. Right? It's a function such that, right, we just restrict the range, right, to a subspace that contains h of x. Right? This contains h of x. So yeah, this is really it. We have finished the Tietze extension theorem. Okay, this is a good theorem, and next time we're gonna start on something new. And hope to see you guys next time. Take care and good night.